The general objective for today's class is students will be able to understand the importance of packing density and concrete rheology. The specific objectives are indicate the importance of particle packing density, represent the need for the calculation of bulk density and void ratio, illustrate the particle interference of aggregates. Before moving on to today's class, we can have a short recap of what we learned in the previous class. In the previous class, we have learnt what is concrete, what are the various materials that are used for making a concrete, what are the mixed proportions, and different types of mixed proportions have also been learnt. Then, what are the various basic tests that should be carried out on the different materials that are used in concrete making. We have also known what is the difference between nominal and design mix, the procedure for how to design a mix of concrete. These are the various things what we learnt in the previous class. The next is, what is this design mix? Design mix is represented as M20, where M is nothing but it is the mix, and 20 is nothing but it is a 28 days compressive strength of cubes. The 28 days compressive strength of cubes will be explained in detail with the following animated video. Compressive strength of a concrete is defined as the ability of concrete to withstand specific compressive forces. The compressive strength of concrete varies on various factors such as water-cement ratio, cement strength, quality of concrete material, quality control during production of concrete, etc. The general sizes of the specimens are of two types. The first one is a cube which is of size 150 into 150 into 150 mm. While the cylindrical specimen dimensions are, the diameter is 150 mm and the height is 300 mm. Generally, the fresh concrete is prepared according to the required grades and respective mixed proportions. Once the fresh concrete is prepared, the inner surface of the mold is greased in order to avoid the sticking of concrete. The prepared fresh concrete is then filled inside the mold in 4 layers. After filling each layer, damping should be done at least 25 times for cylinder by a tamping rod. Once the mold is filled, the leveling of the top surface is done. After a day, the mold is removed and the specimens are dropped into the curing tank at a standard temperature of 27 plus or minus 2 degrees Celsius. After 7 days of curing, the specimen is taken out of the curing tank and it is dried for a while. Then, the specimen is placed on the compression testing machine. The cube specimen is just placed on the bearing plate, while the cylindrical specimen is placed vertically. The instrument is then adjusted such that the specimen is correctly placed on the equipment. The load is then applied gradually over the specimen at 140 kg per centimeter square per minute. The load at which the specimen fails is noted. Thus, the compressive strength of concrete is nothing but it is calculated by using the formula load divided by area. The test is generally done with the help of 3 specimens for 7 days, 14 days and 28 days. The general outline for today's class are: you will be able to understand what is the need for particle packing density, what is the concept behind rheology, And finally, we'll be able to mix a concrete proportion for M20 grade. Generally, we know what is concrete. It is a mixture of many ingredients, which is nothing but cement or cementitious material, coarse aggregate, fine aggregate, as well as water. That's why it is known as a particulate system. In the fresh state, all the materials are in plastic state, that is, it is able to flow. Initially, the coarse aggregates fills the voids between the molds, and there is interstitial voids present in between each and every coarse aggregate. In order to reduce these voids, we use fine aggregate. The fine aggregate fills the space between the coarse aggregates and the gap between the mold. In order to reduce the air voids even more, what we do is we mix cement or the cementitious material with water. Thus, it reduces the air contents in a very larger extent. In natural view, the concrete is like this after it is hardened, where the larger particles are nothing but it is known as the coarse aggregate, and this is the fine aggregate, and the ash colored segments are nothing but these are the cement or the cementitious material. So what is aggregate particle density? We'll be able to know it in a short time. This is a particular system in which the coarse and fine aggregates with the cement contents are present. On top there are air voids present. So the volume of the solids are represented here. On top it is the volume of the pores. The space that fills the volume of the pores as well as the volume of solids is nothing but the total volume of the material. Therefore, the particle density is defined as the volume of solids divided by the volume. This is the general formula which is used in order to calculate the value of aggregate packing density. So what is particle density? Why are we doing it? We'll be able to know it in a much detailed manner. So this is a cubic representation of coarse aggregates that are allocated in a linear manner. In this, if we want to find the volume of a singular element alone, that is a particular spherical portion, we know that the air voids are present on all the four corners of the square. Due to the presence of this, there are lots of air voids present. So the particle density is having a very lower content. In order to reduce this, what are we doing is, we are adding the fine aggregate. Now, if you're going to calculate the volume, in this portion, what happens is, the air voids are getting reduced due to the filling of the fine aggregate inside the coarse aggregate particles. Therefore, the percentage of packing density is increased to a little higher value than the previous one. And finally, when the coarse aggregate, the fine aggregate as well as the cementitious materials are present in concrete, now if you're going to calculate the volume of a single portion, the air voids are much reduced. Now if you calculate the percentage of air voids from the above two figures, we'll be able to see there is very lesser content of air voids present. Therefore, out of these three figures, the particle density has a very higher value for the third figure when comparing to the second and the first one. I think you will be able to understand clearly what is particle density from these three figures. Next, we'll be learning what are the effects of particle packing density. There are two major effects. The first one is, in this, the bigger spheres are nothing but these are the coarse aggregates which are present. The smaller ones are the fine aggregate. In this, we'll be able to understand clearly that the fine aggregates are arranged in a very systematic manner. The air voids between the fine aggregates are very less, but we should note that the air voids between the coarse aggregate as well as the fine aggregate, you are having a large content of air voids present when compared to the fine aggregates. So what happens in this is, There is disturbances in the fine aggregate due to the space it fills between the two coarse aggregates. So the disturbances are very less due to the availability of coarse aggregates. So this effect is known as the wall effect. The next one is, in this figure what happens is the coarse aggregates are present on all the corners and a fine aggregate is present in between. In this what happens is the fine aggregate tends, or it makes the coarse aggregate move to any direction present. So what happens in this particular effect is nothing but the fine aggregate, it disturbances the coarse aggregate. So this effect is known as the loosening effect. I think you'll be very clear with these two effects. In wall effect what happens is the coarse aggregate is disturbing the fine aggregate, but in loosening effect the fine aggregate is disturbing the coarse aggregate and it increases the voids between the two cases. So these in general are the effects of particle packing density. In order to draw a graph, what are we going to do is, in x-axis we are going to plot the volume fraction. A is nothing but it is the coarse aggregate and B is nothing but it is a fine aggregate. In y-axis we will be having the particle density. Therefore, initially when concrete is in the fresh state, it is able to flow. At that particular state, what happens is the density increases, and after certain time when all the air voids or the disturbances and all the effects are getting over, it starts decreasing. So this is what happens initially in all states, but practically what happens is this curve represents the packing density. The red color is the theoretical value, whereas the black color represents the practical representation of packing density. The packing density is maximum as shown in the black graph. The formula for calculating the packing density is dP. It is nothing but the packing density, the mass of the aggregate divided by the volume into the specific gravity of the material that is used. This is the general formula which is used for calculating the packing density. Next, what we are going to see is the concrete at the fresh state. Initially, when the concrete is done, it has the flowability, that is, it will be able to flow. It is nearly in the liquid state or in a semi-plastic state. We will be able to place it into any shape. In that particular state, the concrete has a maximum of 30% of voids present in it. So, in order to calculate the value of cement, what should be used in the concrete mix proportion, we are going to use it with the following formula, which is nothing but 1 minus dP max into 10%, where dP max is nothing but it is a maximum particle density, into 10%, it is nothing but an assumption what we are using in order to reduce the 30% of voids. Therefore, when concrete is placed in molds initially, there will be lots of voids present in between. So, in order to make a perfect mold or in order to make a concrete in a perfect cube, what are we going to do is, we will be using the Weber needle vibrator or vibrating machine. So, in this what happens is, initially when you are inserting the vibrating machine inside the mold, the coarse aggregates, the fine aggregate and the cementitious material, the voids present in between these three, it gets reduced. But at the same time, we should very carefully use the vibrating needle, because if it is used to a very larger extent, what happens sometimes is the coarse aggregate gets settled at the bottom, or the fine aggregate or the cement materials, it gets allocated or lumped into certain areas. So, in order to reduce that, we should use the vibrating machine very carefully, and the cohesion between each and every ingredient should be maintained. Next, we will be seeing the rheological properties of fresh concrete. Rheology is nothing but it is the property of flowability, and what are the factors affecting the flowability is generally learnt in rheology. So, the flowability properties are nothing but we will be able to find it by using the fundamental principles of shear stress and shear strain. We know what is the value of shear stress as well as the shear rate and the shear strain for solids, liquids and for all the other flowing liquids. So what is the goal of rheology generally is nothing but when we are going to study about concrete, initially we'll be learning what are the different states of matter and what are the different ingredients using in concrete and what are its physical characteristics we'll be knowing beforehand. Then the chemistry part of concrete, which is nothing but the hydration equations and the chemical compositions of each and every ingredient will be studied in detail. And finally, by using the basic principles of shear stress and the shear rate, we'll be able to find the rheological properties of concrete. And finally, the engineering and technology is nothing but in order to not to diminish the basic materials, that is fine aggregate, coarse aggregates. In order to save those elements, what are we doing is we are using a huge amount of waste products inside concrete. So in order to learn all these parameters and to use the various techniques, we'll be using the rheology of liquids concept. Now we can move on with the design example mix for M20 grade concrete. The type of cement is taken as PPC. The exposure is assumed as severe. The slump is taken as 65 mm. The maximum cement content to be taken as 450 kg per meter cube. The chemical admixture used is superplasticizer. The size of the aggregate to be used is 20 mm. The specific gravity of the materials are: cement is taken as 2.88, coarse aggregate as 2.74, fine aggregate as 2.65, chemical admixture as 1.145. The water absorption for coarse aggregate is taken as 0.5% and for fine aggregate it is taken as 1%. The various processes that are to be done while designing a mix are: the first step involves the determination of target strength, then the selection of water cement ratio, the selection of air content is to be determined, the selection of water content is found out, calculation of cementitious components are determined, proposition of volume of aggregates are found out, the mix calculations are finally done, and we are doing on with the mix proportion. The step 1 of concrete mix design is to determine the target strength, that is FCK dash. Target strength is the strength of concrete for which we are going to do the concrete mix. Even if the workmanship is going to be very poor, we can get the desired compressive strength, that is the 20 Newton per millimeter square, where 20 means that my compressive strength should be at least 20 Newton per millimeter square or 20 megapascal. The target strength should always be greater than the 28 days compressive strength. For this, the code IS 10262 of 2019 version gives two expressions that are given below, where FCK dash is nothing but the target mean strength at 28 days. FCK is the characteristic compressive strength at 28 days, S is the standard deviation, and X is the factor based on concrete. The first expression is FCK dash is equal to FCK plus X, where the value of X is to be determined from table 1 of IS 10262. As we are designing M20 mix ratio, the value of X can be taken as 5.5. By substituting the value of X, we are getting the value of FCK dash as 25.5 Newton per millimeter square. Now, the second expression is to be solved. The second expression is FCK dash is equal to FCK plus 1.65S, where S is nothing but it is a standard deviation. The value is to be determined from table 2 of IS 10262 2019 version. In this, we are considering M20 mix proportion, where the value of S is equal to 4. Therefore, by substituting the value, we get the value of FCK dash is equal to 26.6 Newton per millimeter square. Finally, the target mean strength is derived from these two values. The value which is having the maximum value is considered as the final target mean strength. So FCK dash is equal to 26.6 Newton per millimeter square is considered as the target mean strength. The second step is to determine the air content. So the nominal aggregate size what we are using is 20 mm. So according to table 3 of IS 10262, for the maximum size of aggregate 20 mm, the entrapped air content is taken as 1%. The third one is to determine the correct water cement ratio. As from figure 1 of 10262 of 2019 edition, this figure gives us three curves in which curve 1 is used for calculating the value of OPC 33 grade, curve 2 for calculating the value of OPC 43 grade, and curve 3 for calculating the value of OPC 53 grade. Here also there is a condition. We are not using OPC 33, 43 or 53 grade. We are using only PPC. So in the note, the second condition is while using PPC or PSC, the appropriate curve as per the actual strength may be utilized. In the absence of actual 28 days compressive strength data, curve 2 may be utilized. So in this case, we are designing for PPC and we are not having the exact compressive strength value for 28 days. So we can use curve 2. In the previous step, we have found out what is the value of compressive strength. It is approximately equal to 26.6 Newton per millimeter square. So this value is plotted and the line which touches the curve 2, the vertical portion, determines the water cement ratio. It is approximately equal to 0.55. So the water cement ratio is equal to 0.55. So we have determined the water cement ratio and this we are going to verify with the IS codal provision recognitions from table 5. The environmental exposure, what we have already known is severe. So for this condition, the maximum free water cement ratio should be 0.45. The value of water cement ratio, according to this recommendations, it should not be greater than 0.45. But the value what we got was 0.55. So the corrected water cement ratio that should be used and proceeded further in the mixed proportion is 0.45. Next, we'll be moving on with the water content. From table 4 of IS 10262 of 2019, the maximum size of aggregate we are using is 20. Therefore, the water content is 186. Here also, we have a small correction. The correction that is to be required by the codal provisions is these values for 10 mm size, 20 mm size and 40 mm size, these slump values are only 50 mm slump values are determined. According to that, we are getting the water content as 208, 186 and 165. So, if the value of slump is greater than or less than 50 mm, the required water content may be increased or decreased by about 3% for each increase or decrease of 25 mm slump or may be established by trial and error process. This is the codal recommendations given in IS 10262. Therefore, the water content what we are getting is 186. The slump value which is to be considered for this problem is 65 mm. So, for 50 mm slump, the water cement ratio is 0. And for 75 mm slump, the water content is 3%, that is increase in 3%. The slump what we get in this problem is 65 mm, which is in between 60 and 75 mm. So in order to calculate the value of water content, we are going to interpolate. You all know how to interpolate a value between a minimum and a maximum value. So by using that process, we interpolate and we get the final water content percentage as 1.8. So this value is substituted and finally we get the increased water content as 189.3.5 kg. This water content value is then it can be reduced with the help of superplasticizers. So as per the codal provisions, if you are using superplasticizer, 1% by the weight of cement can be used. So if you are using this 1%, then the reduction in water content is about 23%. So for example, if you are using 100 grams of cement, 1 gram of superplasticizer can be used. Therefore, there will be reduction of 77% of water in the mix. In the same way, the water content is calculated and finally the water content is found out as 145.80 kg. Next, we will be moving on with the cement content. We know the water cement ratio is 0.45. The cement content is nothing but the water content divided by the water cement ratio, which is 0.45. Therefore, the cement content can be calculated by substituting the values, and we will be calculating the value of cement content as 324 kg per meter cube. Now, we are going to verify the cement content with the table provided in IS 456. The environmental exposure condition is termed as severe. So, for this particular condition, the minimum cement content to be used is 320 kg per meter cube. But at this current problem, we have calculated the cement content as 324 kg per meter cube. Therefore, the final cement content what we are going to use is 320 kg per meter cube. Next step is to find the value of the coarse and the final aggregate volume. As per the codal recommendations of table 5, the maximum size of aggregate used is 20 mm. The zone is considered as zone 2, and for this the value of total aggregate is 0.62. So this value is taken from the code 10262 of 2019, and it has certain corrections also. The corrections is the proportion of volume of coarse aggregate to that of total aggregates is increased at the rate of 0.01 for every decrease in water cement or cementitious materials ratio by 0.05 and decreased at the rate of 0.01 for every increase in water cement ratio by 0.05. So, the water cement ratio is 0.5. The aggregate volume is 0.62. The water cement ratio what we are using is 0.45. From this we can come to a conclusion that the water cement ratio is decreasing. As the water cement ratio is decreasing, the volume of aggregate content should increase by a percentage of 0.01. Therefore, the final volume of aggregate will be 0.62 plus 0.01, which is 0.63. So, finally we are getting the coarse aggregate content as 0.63. We know the total volume is equal to the fine aggregate plus the coarse aggregate. We know the value of coarse aggregate. Therefore, we will be able to find the value of fine aggregate by subtracting 1 minus 0.63, which is nothing but 0.37. That is the final aggregate volume. Next, we will be moving on with the mix calculations. We are using absolute volume method to calculate the mix design. So, we are assuming 1 meter cube of total volume of concrete. We know the volume of entrapped air as 0.01 meter cube. The volume of cement is nothing but the mass of the cement divided by the specific gravity of cement into 1 divided by 1000, where the mass of cement is already calculated. The specific gravity of cement is obtained from the test which is done beforehand before starting the mix proportion design. By substituting the values, we will get the volume of cement as 0.113 meter cube. The next we'll be moving on to the volume of water. We all know the mass of water is all determined in the previous steps. The specific gravity of water is taken as 1. By substituting the values, we'll get the volume of water as 0.146 meter cube. The next one is the volume of superplasticizers. The mass of superplasticizer is already determined and the specific gravity of superplasticizer is already given in the problem in the initial steps itself. By calculating, we will be getting the volume of plasticizers as 0.0028 meter cube. Therefore, the final volume of the aggregate is subtracted from the value 1. So, 1 minus 0.01 minus 0.113 minus 0.146 minus 0.0028 gives the volume content of the aggregate, which is nothing but it is 0.73. Next, we will be moving on with the mix calculations. The mass of coarse aggregate is equal to F into the ratio of coarse aggregate into the specific gravity of coarse aggregate into 1000 gives the mass of a coarse aggregate. The value of F is calculated in the previous step. The ratio of coarse aggregate is nothing but the content or the volume of coarse aggregate, which is 0.63, and the specific gravity is 2.74, which is already given in the problem. By solving this, we will be getting the mass of coarse aggregate as 1261 kg. In that same way, we are finding the mass of fine aggregate. The value of F is just the same which is found in the previous step. The ratio of fine aggregate is 0.37, which is determined in 2 or 3 steps before. And finally, by multiplying, we will be getting the mass of fine aggregate as 716 kg. Now, we are deriving the mixed proportions. We have calculated all the values. Therefore, from it, we are getting the value of cement as 324 kg per meter cube. The water content as 145.8 kg per meter cube. Coarse aggregate as 1261 kg per meter cube. Fine aggregate as 716 kg per meter cube. But still, there is going to be something else which we should do, which is nothing but the calculation for adjustment of moisture content. We know that in the starting of the problem, we have given the water absorption for fine aggregate and coarse aggregate. We have taken that into account because the fine aggregate and coarse aggregate are going to be very dry initially, and when mixed with water, it will absorb more amount of water, thus making the concrete less workable and sometimes leading to complete hydration process. The correction of this water content is really important. That only we are going to do in this step, which is nothing but the adjustment of moisture content. So, for calculating the new mass for fine aggregate, the formula is fine aggregate mass in normal condition divided by 1 plus water absorption divided by 100. The mass of fine aggregate is already calculated as 716 and the water absorption for fine aggregate is already given in the problem. So, by solving it, we will get the value as 709 kg per meter cube. By subtracting the original value of fine aggregate, what we got, we have come to a conclusion that 7 kg per meter cube of water is found to be in excess for fine aggregate. In the same way, we are going to find the extra water for coarse aggregate also. By substituting the formula, we will be getting the extra water content for coarse aggregate as 6 kg per meter cube. Therefore, the final water content or the new water content is the original water content value what we have determined as 146 plus 6 is nothing but the new water entry in fine aggregate as well as 7 is the water excess in coarse aggregate. By adding all these three values, we will be getting the new water content value as 159 kg per meter cube. Thus, by summarizing the mixed proportion, we will be able to get the value of cement as 324 kg per meter cube. The water content, the new water content is 159 kg per meter cube. The new coarse aggregate mass is 1255 kg per meter cube. The fine aggregate mass is 709 kg per meter cube. Therefore, finally the mixed proportion is nothing but it is the percentage of cement is to the percentage of fine aggregate is to the percentage of coarse aggregate is to the water cement ratio. Finally, the mixed proportion what we got is 1 is to 2.19 is to 3.87 is to 0.45. This is how we'll be designing a mixed proportion for M20 grade concrete. In the next class, we'll be able to design a mixed proportion for a higher grade of concrete. Thank you.